You just had a test, and on your test, the first couple questions talked about where is this function differentiable, okay? And they gave you, I don't know, a picture like this. Remember that? Do you? Okay. Let's call this point A. This function, you look at this right here, it is differentiable, meaning I can take a derivative, I can take a slope of a tangent line everywhere, except guess where? That point, this point right here, which we call a cusp or corner, okay? So at that corner, it's not differentiable. It is continuous. What does continuous mean? Continuous, again, the basic.
Like that X axis.
Yeah.
Continuous is where like I can just take my pencil and I never have to lift it up, really. That's just a general idea. And so this is continuous, but it's not differentiable because of that corner, okay? Does that make sense? This is very important for what we're going to do today. Let me give you another picture. Something like, I think this was on your test too.
Yep.
Was something like that?
Something like that.
Something like that. Okay. Yeah, this was a little bit more straighter, but problem is, again, here, this point right here, I would have to draw a vertical tangent, and you are not differentiable at a vertical line. Why?
Because it's too many points.
Yeah, the slope is undefined. Think about it. You are not defined, right? You have no definition of a slope right here. So it's just a vertical line, can't do it. All right, and then just another picture right here. If I had like, I don't know, something like that, okay? And here's the point A. Am I continuous, first of all? No, there's a point where I'd have to jump up. So I'm not even continuous the whole time. But I am not differentiable here. Why? Because obviously I can't take a derivative. Where am I going to take the derivative of? Okay, so it's not continuous. It's not differentiable. Is this all in your head idea making sense, kind of, about when you're differentiable, when you're not differentiable, when I can take a derivative, when I'm continuous? All right. So differentiable means, can I take a derivative everywhere? Is there a point I have a problem? And the main things where you have problems at are these things called cusps or corners. You have problems where you would make a vertical line. There's a problem there.
The point on the second one?
Here?
Yeah.
Right there at that point A. You'd have to draw a vertical tangent.
Okay.
And then you can't do it right here. You can't take a derivative right here either. Okay? And it's not continuous.
But you can take a derivative like other.
Correct. But you could take a derivative other places. Did everybody hear what Jack said? Because once again, he's so smart. Okay.
That's what this is.
Jack, just explain it to us. All right, so let me give you the basic idea of the mean value theorem, which is what we're going to talk about today. This is, I'm going to call it basic idea. Okay, the mean value theorem. So the mean value theorem says that if I have some interval from A to B, okay? And I, first of all, in order to apply the mean value theorem, in order to do the mean value theorem, first things off, you have to be continuous on the closed interval A to B. Meaning every point, including A and B, you have to be able to be continuous. Meaning there's no holes, there's no gaps, there's no asymptotes. You all with me on that one? Okay. Number two, you have to be differentiable. Meaning I have to be able to take a derivative, differentiable, on the open interval AB. I have to be able to take a derivative everywhere between A and B, but not necessarily at A and at B. Does that make sense? Okay, at the open interval, I got to be able to take a derivative everywhere, not necessarily at A and B, very close to A and B, but not at A and B. So I am good right now. This right now is continuous. I can take a derivative everywhere. I have no problem. Perfect. Then we can apply the mean value theorem, which states the following. Then the derivative at some point C, which this again is the derivative of, or this is the slope of the tangent line, is actually equal to f of b minus f of a over b minus a. If you remember doing that, this is the slope of the secant line. So what does that mean for us? Well, that means at some point A and B, if I took the secant line and I took the slope of that line, there would be some point C, and I could take the derivative, I could take and find the slope of the tangent line, and those two would be the same. Why am I drawing parallel lines? What do we know about parallel lines? Same slope.
Zero.
So there is some value C from this derivative that is the same as the slope of secant line of A and B, okay? We say that the instantaneous rate of change, which is this one right here, this is the derivative, the instantaneous rate of change is actually equal to the average rate of change at some point C. And that's what we're looking for. Where is this point C? Find it for me. That's what the mean value theorem does. All right, so I got 4 examples to show you. Some of them are going to work and some of them are not going to work. How are they not going to work? Because they're not continuous the whole time or in that interval. Or they can't take a derivative in that interval. Are you with me on that one? Right. So if you can't take a derivative in that interval, you'd be like, can't apply the mean value theorem. Sorry, boom, done. It'll be great. All right? Makes sense? My function is x squared minus 4x plus 1 on the interval 1 through 5. Okay? So do you all know what this looks like? You should. It is a parabola. Okay? So the first thing you have to do...
Smiley face.
Good job. Okay. The first thing you want to do, and there's like 5 steps to this, is you want to ask yourself, first of all, is it continuous on the closed interval 1 through 5? Meaning, do I have any holes or jumps or anything? Because if not, I'm going to just stop right there. So I'm going to let you all know that, and you can put it in your calculator, but it looks like that. Okay. I'll put it in my calculator right here. So from 1 through 5, here's 1 and here's 5, let's say. Am I continuous the whole time? Yes. Quadratics are always continuous, y'all. We talked about that before, okay, when we do continuity. Quadratics are continuous everywhere. So we've passed test 1. Test 2, though, asks, is it differentiable on the open interval 1 through 5. And again, can I take a derivative everywhere of a quadratic? I can. Quadratics, you can take a derivative everywhere. So that's the beauty of that. So quadratics are differentiable everywhere. Once you've passed test 1 and 2, then you're going to actually start doing test 3, the third, which is applying the actual mean value theorem. So let me do that, and then you can answer your questions. Give me 1 second. So first thing you want to do is find the derivative, which I know you all can do very well. Okay, so what is the derivative of this function right here? 2x minus 4. Okay, so once you pass test 1 and 2, take a derivative. Then step number 4, you are going to find the f of a and the f of b. Now, what does that mean? First of all, what is my a and what's my b? This is my interval A and B. Okay, so I'm going to find the f of A, which would actually be the f of 1. Where do I plug that 1 into? Here or here? The derivative or the original? The original. The original. So f of 1 is actually 1 squared minus 4 times 1 plus 1. Which is -2, correct? Yes, good job. And then f of b, which is f of 5, is 5 squared minus 4 times 5 plus 1, 6. Okay? So, step 3, take a derivative.
So A always X and B's B is Y.
No, A.
Because it could be different.
It's just that's where your interval is. So those are your endpoints on your interval. Okay. All right. So then step number 5, which is our last step, is we're actually going to then apply the mean value theorem. And again, if you look at what you just wrote over here, the mean value theorem says then the derivative is equal to this derivative, the slope of the tangent line is equal to the slope. We have to do this formula part and we have to find that value C. So I always like to write down the formula again. So f prime is equal to f of b minus f of a over b minus a. So the derivative, which I found up here, here's my derivative, 2x minus 4, is equal to, didn't I already find f of b? 6 minus f of a, which is negative 2, so that becomes plus 2, over b minus a. Go back up here. b minus a, what's that? 5 minus 1, which is 4. What is this reduced down to, this fraction?
2.
Yeah. And then solve for x. 2x equals 6. What does x equal? 3. Okay, now, you think you're done, you found the point, but here's what you have to check. Is this point in the interval that was given? Okay, if it is, then that is the value C. This is the actual C value, where the slope of the tangent line is equal to the slope of the secant line. That's what the mean value theorem is all about. Okay?
Let's say if x was 6, what would be the answer?
Then you would no, there is no value in that interval. Yeah. Yes, Jack.
Like the secant line is like touching the 2 point
Correct.
on it, and it's touching at like x is 2 and 6.
Correct. We can get. So again, we're going to find the point C where this works. And I want you, again, if you don't know what this picture looks like, or remember, you can type it in your calculator. So I'm going to type it in real quick for you. To the 2/3. This takes forever. Sorry.
Wait, what?
Boom. Oh, what's the problem here?
That is not going to work.
Is it,
It's not differentiable.
It's not differentiable at where?
Zeros.
what is it?
Okay, but wait.
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 What is your what's under your calculator?
Sorry. Okay. This is why you have to be very careful about what the mean value theorem says, because a lot of students are going to be like, I'm stopping. I see a cusp. I'm done. But you're not paying attention to what it actually says then. Step number 1, okay, and yes, there is a cusp at 0. But step number 1 says, okay, first of all, is it continuous on the closed interval? Yes, my pencil will move the entire time. Yes, okay. Here's where students will get this wrong. Is it differentiable? Watch this. On the open interval of 0 to 1?
Yes.
Yes. Why yes and not no?
Changes on the
Because it's exactly. I didn't close at 0. It's not closed at 0. If it was closed at 0 here, yeah, I couldn't do it. If I shifted this over, actually, if I made this interval between like -1 and 1, I couldn't do it. I would actually stop. So it is a differentiable on the open interval, not exactly at 0. Yes, it is. I can take a derivative everywhere but 0, and that's what that open part means. I can take a derivative everywhere.
If there's a hole in the graph,
And you can do it, yeah. Not if it's in that interval.
there's something.
Wait.
Yeah, it's not continuous, not in that interval. All right, so then step 3, find your derivative. Because it's a yes, yes here. So what is the derivative of f of x?
2/3. Still 1/3.
-1/3, right?
Yeah.
Okay. I do think you have learned you really should rewrite this in a correct form. So this is 2 over 3x to the 1/3. Do you all agree to that? Okay. Once you take a derivative, I would find the f of a and the f of b, and I'm going to call this a and this b. So this is the f of 0, which is 0 to the 2/3. What's that? 0. The f of b, which is 1 to the 2/3. Guess what that is? 1. Okay. And then once you do that, apply that formula. Like some people probably skip 4. This is how I do it. So the formula again says we're finding some value c, of course I'm calling it x, such that f of b minus f of a over b minus a. So take your derivative. Well, you should have this already memorized. Similar to the quotient rule. So 2 over 3x to the 1/3 equals, that right there, equals, this is slope. Yeah, that's all it is. Slope is secant. F of b, which is 1, minus f of a, which is 0, over b minus a. What's that? 1 also. Hey, God bless you. All right, let me do a little algebra for you because I'm still concerned that people don't know how to do this. When you have a fraction equal to a fraction, it's really best to do cross multiplying. Okay, so I would get 2 equals 3x to the 1/3, right? 1 times 2 is 2. How do you get x by itself? Divide by 3. And then how do you undo a cube root or a x to the 1/3? You cube it, somebody said. It's probably Jack. And what does that become? What's 2 cubed? 8. What's 3 cubed? Is 8/27 in the interval of 0 to 1? It is. That is your C value. That is where that is the point where the slope of the secant is equal to the slope of the tangent line. Okay? You're loving it. I know, I can tell. Just 2 more examples and we're done.
Do you multiply by 3 and just cube the other side?
Whenever you want to undo a fraction, you raise it to its reciprocal power. All right. This might help you. This definitely will help you out for some of you who are still struggling on this. Is it continuous? Is it differentiable? Okay. You should all know what this looks like. What does an absolute value look like? Correct. So do we have a problem when we have a V? Yes. We do. All right. So let me show you. Math num abs. Yeah, exactly. Maybe. Let's look. Okay. So here's the graph. You see that right there? Okay. Do you see where it's between? Where's that problem area between? It is actually between 1 and 2, right? Okay, so let me graph this for you. 1, 2, so my V is right here. That is a problem for me. All agree? Mm-hmm. Is that in this interval between 0 and 2? Yeah. So, I mean, let's go through the process here. Number 1, is it continuous on the closed interval? Oh yeah, it's continuous. I mean, I'm going to trace it. I can trace it very easily. But number 2, is it differentiable on the open 0 to 2? No. That right there is a problem within my interval right here. No. Can't. If this interval was shifted, if it was shifted from 2 to 4 or whatever, sure, I could apply the mean value theorem. Yes.
So since it's in the 0 to 2 range, it can't
take a derivative in that range. It has to be able to take derivative at every point in that range. Outside of it or inside of it, yeah. Okay. All right. So here's what you would say. Can't apply the mean value theorem. Done.
Explain the difference between the brackets and the parentheses again?
Okay, the difference of a bracket and parenthesis meaning you can include 0. Okay, it is continuous at 0. It's continuous meaning if you're coming from each direction, you have the same limit. Remember that? Remember doing all those continuity tests? Differentiable means every point. I mean, I'll color it again. Here's 0. At this point, I have to take a derivative. I have to take a derivative. I have to take a derivative. Oh no, but I can't take a derivative, and that's in the interval. That's in here. So that's a big.
2 on the x-axis.
Yeah.
Okay.
All right. One more. All our last example. F of x equals the square root of x minus 4 on the interval 4 to 8. You should all know what this looks like without the calculator. What does this look like? Yeah. So it goes like 1, 2, 3, 4. And where's it shifted, by the way? 4 to the right. So it goes like this. Okay. Now, let's again talk about this whole idea of continuous and differentiable, because you really, I was hoping you would be a little bit better on this, but some people are still not so solid. Is it continuous? Here's 4. Is it continuous on the closed interval of 4 through 8? Okay. Is it differentiable on the open 4 through 8? Yes. Why? But Mrs. Seta, I can't take a derivative. Yeah, but it's open there. It's open. It's not closed at 4 for differentiability. You can still take a derivative. Here's 4. All the way over here is 8. Something like that. You can take a derivative on the open, meaning really, really, really close to 4, but not 4, right? Really, 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 really close to 4, I could take a derivative? Yes, I could take a derivative really, really, really close to 4.
Why couldn't you do one on 4?
Because there's nothing to the left.
There's nothing before it. Okay? So then I can go through and apply my whole entire test. So take a derivative. Let's see. What is the f of x? This is really x minus 4 to the 1/2. Agreed? I had to take a derivative of that. Tell me what it is. 1/2. X minus 4 to the negative 1/2 times the chain, but the chain of that is what? 1. All right, so there's my derivative. I'm going to rewrite that, though. I don't like the way it looks. So 1 over 2 times x minus 4 to the 1/2. So there's my derivative. All right, now I'm going to find f of a, well, so f of 4, and then f of b, which is f of 8. So what is the square root of 4 minus 4? You should know that, but 0. You can take the square root of 0. It's 0. What is the square root of 8 minus 4? 2. Okay. And then step number 5, I just like steps. You set your derivative equal to the slope formula, f of b minus f of a over b minus a. So I'm going to take this, what I have right here, this lovely box, 1 over 2 times x minus 4 to the 1/2. And f of b, which I just found up here, is 2 minus f of a is 0. Over b minus a, that goes back up here. This is a, this is b. b minus a would be what? 4. So what does that actually reduce to? Okay. And again, I really pray and hope you know how to do this. So 2 times x minus 4 to the 1/2 equals 2. What can I do with those two 2's? Divide them out. They cancel. So I have x minus 4 to the 1/2 equals 1. How do you undo a 1/2?
Square.
Square both sides. God bless you. You get x minus 4 equals 1. And so what does x equal?
5.
Is that in the interval of 4 through 8?
Yeah.
And that is the point where you can apply the mean value theorem.
But since you took the square, oh, man.
Okay?
Where does 2 go?
Where did what 2 go? I divide by 2, I divide by 2.
Because we squared it, or we didn't take,
Jack?
How would it like not be
Oh,
between
yeah, that's fine.
4 through 8?
I can't think, I'm trying to think of a time where it won't be, but there's a time
What
where
would that mean? Like,
you just, that is, it's almost like an extraneous root happening. I wish I could think of one. I'll find one. I can't remember. I got to think right now. But I know it's happened. It's happened one time to me that I can remember, and I was like, what?
2 steps.
I think Doesn't always work out. All right, so let me stop this.